Hello everyone, let's discuss planar continuous systems, also known as 2D flows. First, let's discuss the phase portrait in 2D. The solutions of a 2D dynamical system, x of t, y of t, lies on a curve in the xy plane, or also known as the phase plane. In each xy, we obtain a vector field in the phase plane given by x dot y dot, which is called the phase portrait. Now, let's discuss the analysis of linear systems. Consider a 2D linear system x dot equals ax plus by, y dot equals cx plus dy with a, b, c, d constants. We can rewrite this in matrix form as x dot is equal to mx, where x is equal to the vector xy, and m is equal to the matrix a, b, c, d. Note that x star equals 0 is an equilibrium point for the system. We are looking for eigenvectors v1, v2 of m corresponding to the eigenvalues lambda1 and lambda2. If we've obtained them, then the general solution can be written x of t is equal to c1 e to the lambda1 t times v1 plus c2 e to the lambda2 t v2, where c1 and c2 are constants, which can be found using the initial conditions x of 0 is equal to x0 and y of 0 is equal to y0. The qualitative behaviour depends on the lambdas, as the others are just constants. So we need to solve mv is equal to lambda v with v not equal to 0. The eigenvalues are given by the characteristic equation, the determinant of m minus lambda I is equal to 0, or lambda squared minus a plus d lambda plus AD minus BC equals 0. The solutions are lambda 1 and lambda 2 are equal to 8 plus d over 2 plus or minus the square root of a plus d over 2 squared minus AD minus BC. If we let a equal the trace of m, which is equal to a plus d, and d equal to the determinant of m, which is equal to AD minus BC, we can write the lambdas as lambda 1 is equal to a over 2 minus the square root of a over 2 squared minus d, and lambda 2 is equal to a over 2 plus the square root of a over 2 squared minus d. We will show that the classification of phase portraits in the AD plane. Different cases will correspond to lambda real or lambda complex, which is why the line d is equal to a squared over 4 is important, and the stability of the equilibrium points is decided from the sign of the real part of lambda. The stability of the equilibrium points on the 2D is similar to with the 1D case. We will now consider such a classification. There are a few categories of phase portraits, which can be divided into two main classes and a minor class of cases which can be found on the lines of the graph. First, let's consider the case where the lambdas are real, the lambdas are not equal to each other, and they both don't equal 0. This corresponds to a squared being greater than d and d not equaling 0. We have three subcases. First, let's consider lambda 1 less than lambda 2 less than 0. This corresponds to 0, 0, the unique equilibrium point of the system, being a stable node. In the AD plane, this happens when d is less than a squared over 4, a is less than 0, and d is greater than 0. The solution approaches the origin as t tends to infinity and is tangent to the slow eigendirection, which is defined as the direction spanned by the eigenvector with the smaller modulus. Next, let's consider 0 less than lambda 1 less than lambda 2. The origin is then an unstable node. In the AD plane, we need d less than a squared over 4, a positive and d positive. The phase portrait is similar to the stable node, but all the arrows are reversed, pointing away from the origin. Then, let's consider lambda 1 less than 0, but lambda 2 greater than 0. The origin is then a saddle point. In the AD plane, we need d to be negative. Most solutions go away from the origin, so x star equaling 0, 0 is not stable. As t tends to infinity, they approach the eigendirection spanned by the eigenvector v2, corresponding to the positive eigenvalue lambda 2. This line is called the unstable manifold of the saddle point x star is equal to 0, 0. The only case when the solution approaches the origin is when they start on the eigendirection spanned by the eigenvector corresponding to the negative eigenvalue lambda 1. This line is called the stable manifold of the saddle point x star is equal to 0, 0. A solution which is not starting on the stable or unstable manifold approaches the stable manifold when t approaches minus infinity. Next, let's consider the cases where lambda is complex, with imaginary part not equal to 0 and lambda 1 not equal to lambda 2. This is when d is greater than a squared over 4. There are 3 subcases. Now, let's consider the case where the real parts of lambda 1 and lambda 2 are less than 0. Then, the origin is a stable spiral, and in the AD plane we have d greater than a squared over 4, but a is negative. The spirals appear because x of t is equal to a10 e to the lambda 1 t v1 plus a20 e to the lambda 2 t v2, but now a10, a20 and v1, v2 are complex. If we write lambda 1 and lambda 2 as a over 2 plus or minus I times d minus a squared over 4, then x of t is a combination of terms e to the ta over 2 cos the square root of d minus a squared over 4t, and e to the ta over 2 sine square root d minus a squared over 4t. The terms represent decaying oscillations if a is negative and growing oscillations if a is positive. Next, let's consider real parts of lambda 1 and lambda 2 positive. Then, the origin is an unstable spiral. In the AD plane, d is greater than a squared over 4 and a is positive. Now, let's consider when lambda 1 and lambda 2 have real component both equal to 0. Then, the origin is a center. In this case, d is positive and a is equal to 0. The solutions are periodic in this case. The centers are stable, or more exactly, neutrally stable, as they are not attracted to the equilibrium point. These can, in fact, be moved onto the third category of borderline cases. So, now let's consider the other cases. These occur on the remaining lines of the AD plane. First, let's consider lambda 1 equal to lambda 2 equal to lambda, which is not 0. In the AD plane, this corresponds to d equaling a squared over 4, but d not equaling 0. In this case, the origin is a star when there are 2 linearly independent eigenvectors v1 and v2. Any initial condition x0 can be written for some constant c1 and c2 as x0 is equal to c1 v1 plus c2 v2, so the solutions correspond to x0 is equal to x0, which is xt is equal to e to lambda t x0. As x dot of t is equal to lambda of x of t, which is equal to e to the lambda t c1 lambda v1 plus c2 lambda v2, which is equal to e to the lambda t c1 mv1 plus c2 mv2, we have that this is equal to mx. Hence, the solution approaches the origin, or runs away from the origin depending on the sign of lambda, on a straight line generated by x0. When there is only one eigenvector corresponding to the double eigenvalue lambda, the origin is a degenerate node, and the solutions are attracted, or repelled depending on the sign of lambda, tangent to the direction spanned by the eigenvector. If A is negative, the origin is a stable star, or a degenerate node, and if A is positive, the origin is an unstable star, or a degenerate node. Now, let's consider the case where lambda 1 is equal to 0, but lambda 2 is equal to some non-zero real number. This corresponds to the line d equals to 0. In this case, x star equaling 0, 0 is not the only equilibrium point. There is a whole line full of equilibrium points, and the trajectories approach these equilibrium points along some parallel lines, having the same direction as v2 if A is negative, or are repelled if A is positive. Next, let's consider lambda 1 is equal to 0 and lambda 2 is equal to 0. Then, either they are a line of equilibrium points but they do not attract or repel the other trajectories which are parallel to this line, or the whole plane is filled with equilibrium points, which occurs when A, B, C, D is equal to 0. And, as ever, thank you for watching.